Yeah, I'm Chad. I'm a PhD student at Imperial College London, and I'll be talking about this package called Progradio that's written by Eduardo in the crowd over there, and myself under the supervision of Professor Eric Kerrigan. So Progradio is a projected gradient optimization toolbox, and I guess the first thing I'll talk about is what projected gradient optimization is for people who don't know that. So projected gradient optimization is an approach to solving constrained problems where, say, like in the figure over there, you've got this red triangle in which you've got to remain. So that's your constraint area. And then you've got an initial guess, which is the xk point in gray you see over there. So it's like a two-step approach where you start by computing a descent direction using anything like steepest descent or conjugate gradient, Newton's method, anything like that, to get this green arrow. And you solve a step size selection problem to decide how far you move in that green arrow's direction before getting a point that's yk plus 1 you see over there. And then you project back onto your constraint set to get your next iterate. And then you keep doing that until you converge to some optimum. And the reason you'd want to use projected gradient optimization over another form of optimization is because it can be highly efficient in scenarios where it's easy to project back onto your constraint set. So if you've got a box or simplex constraints or some other constraint shape with a cheap projection operator. And so for Progradio specifically, we look at box constraints and simplex constraints. So the reason we're interested in this is because our group does a lot of dynamic optimization, which is this kind of optimization problem where you're solving for functions that minimize an objective over time. So you're not just picking individual points, you're finding functions of time that will satisfy some objective, and then you can discretize these functions to find your solutions, and that gives you really high dimensional problems, which projected gradient optimization is good for. So we do this within the context of what we call JuDO, which is this Julia for dynamic optimization organization we have that has Progradio, Intereso, which Eduardo will be presenting on Friday, and a bunch of other packages in Julia. So now that you know more or less what Progradio is, I'm going to talk about some of the changes we've done since last year's release. Which are adding a Quasi-Wolfe line search, adding support for simplex constraints, and some problem restructuring work we've done to make things easier for the end users. So what's a Quasi-Wolfe line search? Well, whenever you're doing this step size selection process I talked about, where you decide how far to move in the direction of the green arrow, you basically try and find some step that satisfies some conditions. The most common one is the sufficient decrease or Armijo condition. And that's basically just saying you want your function to decrease by more than a certain amount in that direction. So you want to make progress towards your minimum. And that works, but it can be slow in some cases because you can end up finding very short time steps, very short steps that don't do that much progress, or yeah, you can end up stuck in some loops that just don't help you that much. So the second condition people look at is the curvature condition, and when you combine these two, you have the Wolfe conditions. And the curvature condition is basically just saying that because you know that as you get closer to your minimum of your optimization function, your gradient has to be smaller. So you look at a certain reduction in curvature at the point you select as your optimum. So doing a Wolfe line search on an unconstrained problem is very easy. There's lots of established methods to do that. But it's a significantly less obvious thing to do on a constrained problem. And that's why we implement this Quasi-Wolfe line search, which was proposed by Michael Ferry and co-authors in the paper you see referenced there. So I'd love to go deeper into that, but I don't really have the time to. So yeah, I'll move on to how you guys can use this if you use our package. So here's a very simple example where we're solving the Rosenbrock function, which is a standard optimization benchmark. We just define the parameters a and b, and then define the objective function f. We define the function to evaluate the gradient g. And then we define our box constraint through this box object, and then an initial guess, and then we defined our nonlinear program. Then to solve it, we just choose a method to compute a descent direction. So we just choose steepest descent. Then we choose to use a Wolfe line search and try and find a solution. So it's like a simple 3 lines to solve this problem. And then you can see that it goes from taking 139 iterations if you're using a simple Armijo line search to only 3 iterations if you use a Wolfe line search. You will see, though, that the runtime does not decrease substantially. It's only a 10% or so decrease, because every iteration with a Wolfe line search is substantially more expensive than with an Armijo line search. But you start seeing greater benefit in cases where, say, your gradient G is a lot harder to evaluate than here, where it's like incredibly cheap, and because you like have less function evaluations when using a Wolfe line search in general. It will depend on the problem, and some problems are easier to solve with an Armijo line search, but it's an added tool that can be really useful in some situations. So the other thing we've looked at adding are simplex constraints. So instead of just having boxes, we now allow for, along certain dimensions, the states to sum up to some constant value. And while that may seem specific, it's actually really useful in a wide class of problems. So anything like probabilities, or you know that probabilities have to sum up to 1. We also look at things like mesh refinement that we're interested in for our dynamic optimization problems, where we know that basically when you're trying to discretize a mesh into smaller segments, you know that all of these segments have to cover the full range of the space you're discretizing. And sorry. And yeah, also things like when you're allocating a finite number of resources to different tasks or different things, you know that you just have a finite number of resources, so they have to sum up to that. And so we now have support for this kind of problem, which you can like solve easily through our approach. And then we did some other small changes where Progradio now supports any form of abstract array for the states, so it doesn't have to be a vector. You can like feed a matrix input or anything else. We've streamlined the constraint definition, where you can just define a box this way as like a lower bound and an upper bound. And then we've abstracted algorithms to make it easier to specify what combination of descent direction and line search you want to use in a pretty easy way. So yeah, that's it for what we've done so far. In the future, we want to add integration with MathOptInterface.jl to make it easier for other packages to use Progradio, such as like Jump or anything like that. We want to expand our work to more general constraint functions, so we tackle simplex and box constraints explicitly through projected gradient optimization, and then use primal dual barrier functions for more general constraints. And then extend the Quasi-Wolfe line search to simplex constraints. We currently only support it for box constraints, and then add more search directions, such as quasi-Newton directions. So thank you, and
thank you, Jad. Maybe we have time for one very short question. Yes, please.
Yeah. Yeah, you have to supply some method to evaluate the gradient. Oh, sorry, microphone. Yeah, you need to like define how you evaluate the gradient. It can be explicitly. You can like define some other way of evaluating the gradient there, but you just have to choose how you evaluate the gradient. You can do like finite difference or something if you want. Yeah. Yeah, any function like g exclamation mark that will return the gradient at that point would work. Yeah, no, maybe.
Thank you. Maybe another question, yes?
As long as you're starting from a valid initial condition inside that box, it might be a very small step, but there will always be a step. Well, as long as your function is continuous and like well behaved and stuff, like there are some assumptions on the function, but yeah.
Thank you. Well, let's thank the speaker again.